Hello, everyone. A very good evening to all of you, and we hope that you're doing well and safe. Welcome you all to another episode of Tech Talks 101 powered by F Code Labs. And today we will be discussing the use and application of analog computing to solve technology based problems. For this, we have a very special individual who graduated from the University of Moratuwa in 2016 and worked for Synopsys Sri Lanka as a corporate application engineer. She currently lives in the US, expecting her PhD from Florida National University. We have Ms. Hasantha Malavipathirana with us today. Hello, Ms. Hasantha. How are you doing?
Hello, Rishan. I'm doing great. Currently I'm in Florida, Miami. So it's sunny today.
Awesome. Great to hear. Yes, so it is a privilege for us to have you here today, Ms. Hasantha. So moving on with the first thing that we want to know about you. Ms. Hasantha, can you tell us a bit about yourself and your academic background?
Yeah, sure. So currently I'm a PhD candidate at Florida International University in electrical engineering. And I'm working on designing mixed signal integrated circuits for scientific computing, array signal processing, and signal intelligence applications. That's basically my research. And currently I got my master's in electrical engineering from FIU. And before coming here, I graduated from University of Moratuwa back in 2016 from the Electronics and Telecommunication Engineering Department. There I gathered a lot of knowledge and experience, and my final year project was designing application-specific integrated circuits for 100 Gbps Ethernet physical coding sublayer. After graduating, I worked as a corporate application engineer at Synopsys Sri Lanka, and then I briefly worked as a lecturer on contract at the electronics department. All those, they gave me a lot of experience and knowledge. And going back a little further, I have several schools. I have 4 schools. My primary education was in Telejula Royal College. And then I moved to Kandy for some time. I was studying at Dharma Vikram Balika Vidyalaya in Kandy. And then I was at Sujata Vidyalaya Matara. And I did my advanced level in Devi Balika Vidyalaya. So all these schools, they were amazing places. They gave me a lot of knowledge, and they made me to the person who I am today. So that's my academic background. So looking back there from the start, so it's a long way from being a kid to coming here. So everything is a good experience.
Great, awesome. That's great to hear. All right. So can you tell us what made you enter this field? Is there a specific reason for it?
I would say it's the passion for science. Broadly speaking, I was inquisitive and I loved science and how things work as a kid. And that is the passion for me to come into the engineering field. But specifically, so there's an interesting story as well. So I love this science fiction. So my main goal, my dream was to work on these complex projects so that someday if we can make science fictions a reality, the good ones a reality. So that was the dream behind that. But after coming to engineering, so it's where we push forward the technology. So basically the love for science fictions made me come to engineering. And now when I focus on the research I'm doing, currently I'm working with the analog circuits. So that is mainly the core in electronics design. So you're working with transistors and building circuits all the way from small transistors. So that is an interesting field, and that that interest is what made me come into this field.
Yeah, that story sounds very interesting. Yeah, so we heard that you were involved with complex research recently. So can you tell us a bit about the problem statement that you want to address through this project?
Okay, so broadly speaking, the problem is the impending performance saturation in computers. If I go a little deeper, so we know that mainly the advances in computing is fueled by the evolution of VLSI technology. That means transistor size goes down and the transistor density in a chip keeps increasing. It doubles approximately every 2 years. And along with that, chip power consumption is going down. Because of these aspects, we are seeing very large improvements in computing. But when you look at the future, this is not the case all the time. Uh, and there are some impending performance saturations in computing technology, mainly because when you go to smaller process nodes, there are problems like leakage power in transistors, and the power consumption is increasing. Power consumption is supposed to reduce, scale down, but it's not scaling down at the rate that is required. So, and also digital computers are facing limitations in clock speed and the transistor density and power consumption. So there are some limitations, and the researchers are looking into different ways to tackle these problems, all the way from computer architecture, circuit design, and even down to a device fabrication. So the problem is this performance saturation, and we are trying to approach this problem in the perspective of a circuit designer.
All right. So listening to that, what I realized was how passionate you are about what you are doing. Yeah, so moving on, let's dig a bit deep into it. Can you tell us about the solution that you propose through your final project?
Yeah, sure. So it is not like the exact solution. So we are exploring different options. Basically, what we propose is to improve computing performance using analog circuits. I must emphasize that we are not trying to replace digital computers with analog computing. Instead, we are exploring different methods to use analog circuits to solve analog-friendly problems. There are certain types of problems that we can accelerate using analog circuits. For example, there's an application domain called scientific computing. In scientific computing involves solving ordinary and partial differential equations to model physical phenomena. For example, it models systems like systems in electromagnetics, it's used in climate modeling, and in applications like modeling plasmonic oscillations in nuclear reactions. So there are big problems, and people use even supercomputers to solve these problems. And the issue is these equations. Say this, yes, I'm solving a problem that involves partial differential equation. That means it's an equation that models a system. It can a problem that changes with time and space. So when we solve this kind of equation in a digital computer, the normal approach is to discretize the problem in time domain and in the spatial domain. So when we solve these equations in digital computers, sometimes it can take a lot of time, maybe several months, several weeks to solve a complex problem, and consumes a lot of energy. But it is not optimal, because partial differential equations are inherently analog in nature. The time evolution, so these equations models the time evolution of a system. So the time is continuous. We don't have to discretize it. But if you solve this in a digital computer, we have to discretize it. But if we solve it using analog circuits, we don't have to discretize the equation. We can directly map these equations to analog circuits. There are some, even for example, the simple capacitor can perform the integration, and we can use inductors to perform differentiation. And so it's the simplest form. So what we propose is use analog circuits to solve some of these problems, and it helps to accelerate the solution.
Ms. Hasantha, can you elaborate a bit about how you solve differential equations using analog computing? I'm sure the listeners are curious to know about it.
Okay, sure. So I will focus on our approach. So there are several approaches to this. When you solve differential equations using analog circuits, some researchers directly map these equations into analog circuits using integrators and integrators, resistors, capacitors, resistors, inductors, and those passive circuit elements. And there are another approach like using operational amplifiers and other transistor-based circuits to solve these equations. So our approach is called continuous time analog computing. There we start with this equation and then solve this find a mathematical model that solves a specific equation. There are different algorithms such as finite difference time domain methods, finite element methods. These are the methods, these are discrete methods that you usually use to solve differential equations in a digital computer. What we do is we start with this kind of a method, finite difference time domain method. First, we discretize, we model the whole equation in a way that it is suitable to solve in a digital computer. Then what we do is, I said analog is continuous time. So what we do is we design an algorithm that is continuous in time. If we say a discrete equation, it has a time. So when you say discretize, that means there are time steps. So for example, if somebody is familiar with this central differencing scheme, when you want to solve a simple differential equation, you have time step in an equation. Time is not continuous. So what we do is take the time continuous. We model this time discrete time step using time delay term. That time delay, we can build that time delay using an analog circuit. Usually it's called an all pass filter. So it's a delay element. We first start with the equation, then make it discrete, and then again we make it continuous by mapping the time difference into a time delay term. So once we have this continuous time algorithm, then we move on to defining a computing architecture that can map this equation. So we use operational amplifiers, analog multipliers, programmable gains. So there are different circuits involved in this. So we build this computing architecture, and once we have a good architecture, so then only we go to analog circuits. So that part is like we are building an integrated circuit. So you use software like, so we use Cadence software. So it's a analog, it's a EDA, electronic design automation tool that you use to design schematic and then do the layout. So what we do is, once we have the architecture, once we have the idea for all the circuits we need, we go to the software, and using transistors, we first do the simulation. So first we design analog circuit each one by one. Like we design an op amp, design the all-pass filter, design analog multiplier, adders, different subsystems. We design them and then we do the simulation. Once everything is simulation is fine. Once everything is verified, in this stage we are also comparing the simulation results with the digital computer, so that we have to we should be sure that the solution we are producing is accurate. So to do that, we compare it with the digital computer. So once the solution, like the simulation, is clean, then you go to layout. In in IC design, in analog IC design, once you have the schematic, then you go to layout. So you start with the transistor layout. So it's like we have a transistor model. Then when you go to layout, you have to draw everything. Like transistor is composed of we know that it's CMOS. So CMOS, they are source, drain, gate. So there are models, there are drawings with that pattern. So we draw the schema, draw the layout, and it's kind of a time-consuming process, but it's interesting. So you have to consider about the electrical resistance. There are design rules we have to follow. So it's a drawing actually. So once the layout is done, we have to send it to fabrication. So that part, so in our process, we used TSMC 180 nanometer CMOS process. So once we did the layout, we send this layout for fabrication. We send it to TSMC, and they fabricated the chip and send us back. So once we have the IC, we test it, and finally we confirm that the solution is correct and compared with the digital computer. So that's basically the process of that.
All right, great. So that answer had so much that the listeners can gain, and that was a very helpful answer. So thank you very much, Ms. Hasantha. So Ms. Hasantha, can you tell us about the current status of analog computing and where it stands in the technology field at the moment?
So analog computing is not a popular form of computing. It's not, I don't say it's commercial yet. So it's a research field. So people do different research in different domains, such as CMOS circuit-based analog computers, in-memory computing, and metamaterial-based computers. So if you take CMOS-based computers, still it's in the research domain. So CMOS-based computing, digital computing is what we use, what we see. There are researchers trying to use analog circuits to solve some of the problems. So we are doing research using CMOS analog circuits to solve partial differential equations. And if I say the progress, it's like there's one research in our group. We published that we for solving Maxwell's equations, we have a analog IC that works 400 times faster than the GPU while consuming 1,000 times less power. So that is a demonstration, but still there's a long way for analog computers to go. And there are other researchers like in Columbia University. They perform research on analog computers, building analog CMOS circuits to solve differential equations using analog integrators and different other circuit blocks. And there are also researchers conducting in-memory computing based research. And also that domain is somewhat commercialized. There are startups like Mythic who push forward in-memory computing based architectures for machine learning accelerators. And also there are other researchers like who are working on metamaterial based computers. It's like they are trying to solve equations directly on the material itself. So it's not a circuit exactly. They utilize the material itself. So it's a research that is going on. So all this research, I mean, it's interesting field that is moving forward. But there are a lot of things to learn, and there are a lot of boundaries, limitations that we have to push forward. So I would say currently analog computing is a emerging research area that people are working to push forward.
Yes, awesome. So, Miss Hasantha, I mean, people or youth might have different opinions about digital and analog computing, right? Some might say digital computing is better, some might say analog computing is better. I mean, both are good in two different ways. But for this specific project, why did you choose analog computing over digital computing?
Yeah, so again, I must say that it's kind of two different domains, analog and digital. So what ultimately what we propose is a analog core processor that will help digital computers to accelerate certain types of problems, such as these differential equations and even in machine learning. So we choose analog because of some of the advantages. That means for example, the application I explained in scientific computing. So these differential equations are continuous in time. So analog can map this continuous time domain, and uh, because it is continuous in time, analog is a good fit for real-time computing, and also it is not limited by the clock speed limitations. So that is one advantage. And on the other hand, analog is continuous value. That means it's not discrete or sampled. So ideally we can represent a multiple in a single wire. So if you take a circuit, the interconnect density is reduced because analog signal is a real number. So it's not, it's like representing multiple bits encoding multiple bits into single wire. And there's another advantage, analog circuit architectures uh, is a good fit for parallel computing. They can represent massively parallel architectures. So that's why we selected analog. But along with that, there are some disadvantages as well. The main limitation is analog it has less accuracy and less it's not very scalable. For example, the accuracy of analog computer is mainly around 8 to 10 bits. When you compare it with the computers we are using, the double precision arithmetic is 64 bit. So analog is nowhere near that precision. That's why we are proposing these analog computers only to problems that are not very. So we propose them to be used in problems that do not demand very high accuracy, like in matrix vector multiplications and machine learning related problems. So ultimately, the goal is a hybrid computer, so that analog will produce an initial solution or something like a guess that helps to speed up the overall system in the digital computer.
All right. Okay. Yeah. So, Ms. Hasantha, what is the use of differential equations in the field of scientific computing?
Sure. There are several. So if we actually scientific computing use differential equations itself. It's like there are applications like computational fluid dynamics, computational electromagnetics. So in all these domains, differential equations models a physical system. So when we want to simulate a physical system, like for example, if you want to simulate the performance of an antenna, so say we design an antenna to be used in the iPhone, like in a mobile phone. So before go ahead and manufacturing them, we have to simulate it. First, we like simulate, and then we optimize the parameters. So when we simulate a system, we model that system using differential equations. And another big application is like in climate modeling. So we have to predict the climate, and like we have to predict the progress of phenomena like hurricanes. So in that cases, there are fluid dynamic equations. All those are partial differential equations, and they model the system. You have to solve these equations to model the accurate physical phenomena. So that's the main use.
All right. Okay. So I hope the listeners got to know a lot about cut that part. Okay. All right. So I hope the listeners got to know a lot about differential equations in the field of scientific computing. Ms. Hasantha, can you suggest some resources where our listeners who would love to read more about analog computing can refer to?
Mm-hmm. Yeah, sure. So when we say analog computing, there are several different domains. So I was talking about the analog circuits. So there are different domains, and there are like CMOS circuit-based analog computing, in-memory computing that use memory stores, and there are also areas like metamaterial based analog computing, optical computing. So Google Scholar is the best place to find more information. Like there are research papers in these domains, and also it's a good idea to refer to. So I will talk about the main journals in this in electronic design in these analog circuits. So there are some journals like Solid State Circuits Journal, Transactions on Circuits Journals, and conference proceedings like ISSC, International Solid State Circuits Conference, ISCAS, International Symposium of Circuits and Systems, and CICC. It's a conference like a custom integrated circuits conference. So if you read into the proceedings of these conferences and the latest publications in journals, it's a good resource to keep you updated about the current research going in these domains, mainly in analog circuits. So I guess research publications is the best method.
All right, great. So anyone who is interested to learn more or refer about analog computing can refer to those resources, which would be really helpful for all of you. Yeah, so with that, we have reached the final question that we have for you, Ms. Hasantha. Can you tell us a bit about the emerging trends in analog computing and other related technologies?
Yeah, sure. So as I said, analog computing has different domains. There's CMOS circuit-based, in-memory computing, and metamaterial-based computers. So the main trend is for AI. It has so this in-memory computing or the memory store-based computers are finding a lot of applications in AI and machine learning related problems. For example, people are trying to represent the machine learning computations like matrix vector multiplications using memory array type computers. That is part of analog computing, and there's a main trending application. And also there are trends in metamaterial based computers. That means they are the artificially engineered optical materials. So these materials can represent operations like integration and differentiation. So if you pass a light wave through some material, the output would be the integrated integration of that signal. So there are research like that, and there are applications in optical computing as well. So I would say the main trend is for AI. So there's a lot of computation needed and it's a trending research.
All right, great. That sounds really interesting. And I'm sure there are so many people who would love to get to know more about the emerging trends in analog computing and other technologies. So, with that, we come to the end of today's episode of Tech Talk 101. And I would like to take a moment to thank Ms. Hasantha Malavipathirana for accepting our invitation and taking the time off your busy schedule to join with us today. It was indeed our privilege to have you here, and the episode was very informative. And I'm sure the listeners learned a lot about analog computing and its users and its application as well. So thank you very much again, Ms. Hasantha. And on behalf of everyone, I would like to wish you all the very best for your future endeavors. And to all the listeners out there, thank you very much for tuning in. And we hope you got a lot of information and insights from today's session. Stay tuned for more interesting episodes. Until then, good night and stay safe.